some really cool new chips on the market these days. You know how you've always liked putting an FPGA next to your processor? Well, it's just like chocolate and peanut butter. They have put those two cool things together in one package, and the result is better than the combination of the two separate chips. You can do all kinds of amazing things, like accelerate parts of your algorithm and hardware, integrate new peripherals and other connectivity functions, and even do some pretty impressive DSP. But with several of these new SoC FPGA devices to choose from, how do you know which one will work best for your application? Hi, I'm Amelia Dalton, host of Chalk Talk, and I'd like to study the architecture of any SoC FPGA I was considering for my design. Luckily, I have Todd Koelling from Altera here today to help walk us through that process and to see what things we need to consider when choosing an SoC FPGA for our design. Before we get started, remember to click the link. There you can download a free white paper that further expands on this topic. Hi, Todd. Thank you so much for joining me today.
Hello, Amelia. It's great to be here.
So, Todd, we've been hearing a lot about SoC FPGAs for a couple of years now, and they sound really exciting. But I'm curious, how's it going? I mean, are they taking off as fast as people have predicted?
Absolutely. They're really doing great, and we're seeing them take hold in many applications, becoming the new standard for those types of applications. We've also established many development kits. We've got a full range of development kits, as you can see here, from both Altera and our partners, as well as SOMs or systems on modules, which people can use for both prototyping and production. In fact, we've shipped over 14,000 development kits already, showing the uptake on this, which has just been incredible.
Yeah, that is.
And we've got well over 1,000 customers designing this in all geographies around the world. So the response has just been tremendous and just continues to grow.
And where there are processors, there must be operating systems, right?
Absolutely. That's a great point, that you not only need the hardware, but you need the software to go with it. And so for the Altera SoCs, we actually started with a target of 4 major operating systems, but that has quickly grown to over 18.
Wow.
And more on the way as we looked at different businesses and markets, and customer demand has just made this explode as well. So very well in place in terms of the software.
Okay, cool. So it seems like there are a lot of pieces that have to come together in an SoC ecosystem with all these moving parts, but this isn't just Altera walking it alone, right? There must be other partners involved in this effort.
That's right. And so we've gone out and equipped a whole team of players worldwide that are on the Altera team to help you with your designs.
Cool.
In terms of not only the design kits and SOMs that I just mentioned, but also IP and software or any design services you might need. There's someone who'll be in your neighborhood who could help you out and get your design to market quickly.
Yeah, I'm not really surprised that there's a high level of excitement, and the ramp up has been great with these new devices. SoC FPGAs obviously bring a lot of new capabilities that designers really haven't had access to before. But that brings up an important question, I think. There are multiple options out there that combine processor subsystems with FPGA fabric. Now, how do I know which one to choose for my application?
So that's a great point, that on the surface, many of these SoC FPGAs look the same, with a processor, maybe even the dual-core ARM A9,
right,
as well as the FPGA logic combined. But it's a lot more than that. And Amelia, through working with these thousands of customers that I just mentioned, what we've learned is that architecture matters, that it's not just simply bolting those two pieces of the chip together, but they've got to have all the right interfaces and communications and protections to make the system work. And so that's what I'd like to do today, is actually walk you and our listeners today through 3 key areas that we've discovered in this process.
Excellent.
The first is around memory performance, second around memory protection, and then last but not least, let's take a look at system debug.
Excellent. Now, Todd, let's circle back a second here. That first thing you mentioned is memory performance. Let's dive into that one a little bit.
Okay. So to do that, we'll take a look at 2 SoC FPGAs.
Okay.
The key difference here, the one on the left has a 400 megahertz memory bus interface, whereas the one on the right has a 533 megahertz memory interface.
Okay.
We'll run both of them at 667 megahertz to keep that neutral. And which one would you think would have the better performance?
Wait a second, Todd. Is this a trick question? I'm going to go with the 533 megahertz version.
Well, that's a good guess, and I think pretty much every engineer would guess that. But this is a case where architecture matters, and you've actually got to look deeper.
Oh,
so
okay.
Let's do that and take a closer look at this memory interface.
All right, cool. Let's check out some details.
So here's a block diagram of a Cyclone 5 SoC.
Okay.
And just to orient everyone quickly, we've got the FPGA logic up on top of the device.
Right.
The processor system is over on the right in the middle. There's a variety of peripherals along the left and the bottom edges, and then a whole bunch of interconnect in the middle.
Okay.
And to discuss memory performance, the first thing I want to look at is this section circled in red. And these are the SCU, or the Snoop Control Unit ports.
Okay.
Now, the ARM architecture comes with 2 of these standard. And for performance reasons, when our architects looked at this, they decided it was best to route both of those to the L2 cache for the maximum performance.
Okay.
Now, other SoC FPGAs actually route one of those SCU ports to the L2, but they route another one to the on-chip memory. Now, what's the benefit of that? Well, in our Altera SoCs, because we put 2 of these ports to the L2 cache, we could only fit in 64 kilobytes of on-chip memory. By routing another one of those ports to the on-chip memory, the SCU ports, that makes it possible for 256 kilobytes of on-chip memory.
Okay.
So that may be helpful if you're doing a real-time design,
Right.
but there's many other factors around a real-time design as well, in terms of the type of processor you're using, ECC protection on the NAND flash, and things like that. It doesn't end there.
Gotcha.
So when we looked at this trade-off, we decided it was best to keep both of those for the L2 cache.
Okay, cool. That covers cache, but what about the external memory interface?
Well, not all DRAM memory controllers are created equal.
Right.
And here you can see how we've developed the Altera DRAM memory controllers over the years. There's a lot of details in terms of the scheduler, the command and data reordering, and the bank management that we've improved over the years. And we're now up to what we call our Generation 3, which is used in the Altera SoCs.
Okay.
So this likewise can really affect the throughput and performance of your external memory.
All right, Todd, everybody's architecture is best in PowerPoint. But how can we get some objective measure of any of this?
That's a key point. Let's turn to an industry standard benchmark called LMBench. And LMBench is very memory intensive. It's widely regarded in the embedded market and across the industry. And so this is a good referee, if you will, to get just a normalized look at memory performance.
Excellent.
And if you're interested in running this on your own, it's a publicly available free benchmark available at the URL on this slide.
Okay.
So when we run that, these are the results that we get. So, Amelia, let's look at the diagram first. So on the left-hand side, you have your megabytes per second. So obviously higher is better there. We want as much throughput to the memory as we can get.
Right.
And then across the bottom, we're showing the data size in terms of megabytes. Or since we have multiple decimal points there, it actually ends up being bits at the beginning.
Right.
Now, what you see here is there's 3 prominent areas to the curve. At the beginning, it's running out of the L1, and so it's running very fast there.
Yeah.
And then it kind of falls off as we go down to the L2, which in this case for both of these devices is 512 kilobytes.
Okay.
And then once we get past the 512 kilobytes, it kind of levels off as we're going out to the main memory.
Right.
Now, getting back to our contest between the 2 chips here, as you can see that the blue chip, the SoC FPGA-A, actually has a better memory performance starting with the L1 section versus SoC FPGA-B. And then it gets most pronounced in that middle curve there,
Right.
which, if you'll remember, that's the L2 cache.
Yeah.
And so that's where the Snoop control units that we just talked about are coming into play. And that's where you see the performance benefit of having both of those ports going to the L2. Then as we go out to the main memory, again, you would have expected that the 533 megahertz bus interface would outperform in SoC FPGA-B would outperform the 400 megahertz interface in SoC FPGA-A.
Right.
But due to that intelligent memory controller, we see that the performance is actually comparable there.
Aha.
So this is a great example then of how between the architecture features in the L1, L2 cache, as well as the DRAM controller for your main memory interface, can improve the performance.
Okay, I now understand that memory frequency doesn't tell me the whole story in these kinds of things.
That's correct. As we had expected, it would have been the 533 megahertz bus speed, but it turns out that actually the 400 megahertz in some cases outperforms or at least equals the speed of the 533 megahertz interface chip. And as you might have guessed, the SoC FPGA on the left, the SoC FPGA-A, is the Altera chip.
Ah, okay, I was starting to get that picture. It also seems like my system power might benefit from this as well, because memory is a big component of my total system power, and I am able to get more memory performance at a lower frequency. Wouldn't that help my overall power?
Absolutely. That's the big benefit here, is that you could run your memory, which often takes a large amount of power in your overall system power budget,
right,
at a lower frequency, and that's going to save you on the power. It may save you on cost too, but that depends on the DRAM market at that day.
Okay, cool. So the second big thing you mentioned was memory protection, right?
Mm-hmm. Not only do we want fast access to the memory, but we want to make sure that the contents we get there are going to be reliable. So let's start with a look at this new SoC FPGA system architecture. And you can see in the past, we may have had a separate CPU and an FPGA, and each one of those would have its own dedicated memory.
Right.
Now, with the SoC FPGA, as shown there on the bottom, we get better performance, lower power, lower board space, etc. But also, we can share the memory then between those two devices, between the processor and the FPGA.
Right,
so
okay.
that likewise has a cost and board space benefit as well.
Now, with this shared memory part you just highlighted, it seems to me like that would be important with all the things we want to do with an SoC FPGA architecture.
That's correct. It's very advantageous for not only cost savings, but just implementing accelerators and other things like that that could benefit from using that shared memory. So there are some considerations here, though, if we take a closer look at this, that, again, we've learned and I want to walk you through.
Excellent.
So let's say we have some FPGA IP, an accelerator or some sort of other peripheral or master in the FPGA space.
Okay.
And we want to give it some of this shared memory. So we can dedicate a portion of that shared memory space to the FPGA IP.
Right.
But as you know, we also have the processor accessing that memory space. And we don't want that FPGA IP to accidentally go and mishandle some of the processor dedicated space, such as the OS or drivers or other important application data. That would not be good.
Yeah. It would not be cool for our FPGAs to go willy-nilly trampling all over the OS. So how do we accomplish this and protect our memory?
So to do that, again, you've got to have an intelligent memory controller.
Right.
And in this case, at Altera, what we've done is built in that memory protection into the DRAM controller itself.
Ah, okay.
So it can make sure that the processor doesn't mess up the FPGA space or the FPGA doesn't get in and mess up the processor space.
So, can you give me some more details on how that's accomplished?
Yeah, so how we implement that in the Altera SoC FPGAs is, number one, we support the ARM trust zone security, and most SoC FPGAs do that, and that's a great way to do it. But in our case, though, we actually get it down to a 1 megabyte granularity boundary versus other SoC FPGAs have a 64 megabyte boundary. But though the trust zone is great, that's just one memory area. Odds are you're going to want other portions of memory protected in this multi-master sort of environment.
Right.
So to facilitate that, we have 20 user-definable protection rules.
Okay.
And you can implement those, defining specific address ranges and so on, to give you these different memory spaces that are protected. Of course, all these details are in our handbook if you'd like to look at that.
Okay, great. So what about protection of the memory contents itself?
Right. So once we get that data, we want to make sure that it's reliable. And as the memory size in embedded systems gets larger and larger, the likelihood of a bit flip from gamma rays or alpha particles goes up.
Right.
And so that's just a reality that we need to be cognizant of and protect for. So if we look at the external DRAM, there's a main thing you can do there is what's called error correction code, or ECC. And in our case at Altera, we've implemented single bit correction and double bit detection, for those of you who already know something about this. So we actually investigated this and wrote a white paper in conjunction with Micron Technologies, the memory maker, and looked at this potential effect in a system. And Amelia, it's really all about probabilities. We just got to look at the likelihood that one of these alpha particles is going to hit our device and what might happen.
Right.
And so to do this, and this is detailed in the white paper, we extrapolated what a higher bound and a lower bound probability would be for an event like this to occur.
Cool, okay.
And we look at what the mean time before failure and fit rates would be if it had no ECC versus ECC in the system. So as you can see here, with the higher bound with no ECC is an MTBF of 979 hours, which is fairly frequent. Certainly want to do better than that. However, with ECC, we see a dramatic improvement to 10 to the 18th to 10 to the 21st years. So just a huge improvement by implementing ECC.
Yeah.
And so we worked through this with one of our major industrial drive customers on what's the system impact of this ECC. Yeah, these are theoretical fit rates, but when you get systems out there in the market, what's the impact?
Right.
And the key here is this table just shows for one system. Well, what if you have hundreds or thousands of systems out there?
Exactly.
And then your fit rates go up very, very, very quickly. And so when this customer looked at that, they immediately decided that they had to go with ECC mandatory across all their systems.
Ah, okay.
And lastly, I'd like to point out that in terms of our architecture at Altera, we don't just implement the 16-bit and 32-bit ECC on the external memory, but also many other parts of the chip. So the level 2 cache, your on-chip RAM, even the Ethernet Max and USB controllers have this ECC functionality built in. So throughout the data path, we're watching the data, we're protecting that as best we can, and flagging you if there is an unwanted error that can't be corrected.
Phew, okay. My memory's safe.
Absolutely.
All right, let's shift gears a little bit and talk about debug. There's a lot going on inside one of these devices, and occasionally I've found a bug or two in my designs. Occasionally. Now, how do we get inside there to debug? Is there a tiny logic or bus analyzer or something?
That's a great point, that we all wish our code would be perfect right off the bat,
Right.
but seldom it is, and we've got to go in and sort it out. To address this, first of all, at Altera, we set up a strategic partnership with ARM around the tool side. Now, many people have purchased the ARM cores and work with ARM closely on that side, but we also have a very strategic relationship with them on the software side.
Ah, okay.
And what we did is took their industry standard DS5, Development Studio 5 software toolkit, which many people are familiar with and is very well known, very good multi-core sort of product, and built a specific edition for Altera SoCs, which looks at both the processor and the FPGA side at the same time. And so with this DS5 Altera Edition toolkit, you can see both of those sides of the chip at the same time, and even when the FPGA changes, the software will automatically register that and update your view of the device. And that's what we call FPGA adaptive debug technology.
All right, cool. Now, that's the software side. What about the hardware side?
Right. The software has to really fit hand in glove with the silicon. And in this case, we've put the right hooks into the chip itself to give you the maximum visibility and performance in terms of debugging the device and the system to get it to market quickly.
Excellent.
And so I'd like to go deep here again and dive into a key block that we put into the part, which is called the system trace macrocell. So if we go back to our block diagram of the Cyclone 5 SoC, you can see, or actually you probably can't read those letters there, which say STM, circled in green. And that stands for the system trace macrocell, which is the key hinge factor to our debugging process.
Oh, cool. There is a tiny logic analyzer. I was just joking before. So what does this, you called it a system trace macrocell, look like?
All right, let's dive into that next and a little deeper.
Okay.
This shown here is the Altera implementation of the system trace macrocell. We won't go into too much detail here, but just to give you a quick walkthrough of this. In general, what's happening is our data is going to flow from the left to the right.
Okay.
And all our FPGA and other system data is going to come in on the AXI interconnect. and that's a dedicated 32-bit bus as shown in the block diagram we just looked at.
Okay.
Then towards the lower middle there is the processor subsystem, and each one of those cores in the processor, in this case 2 cores, has a program trace macrocell that's going to track our program execution data.
Okay.
And both of those, the data from the system goes through the STM, and the processor data goes into this funnel, which then creates a stream of debug trace data that goes into the ETF, or embedded trace FIFO. And that FIFO is 32 kilobytes, so it can hold lots of trace data.
Yeah.
Then from there, in that kind of the reverse mux there, that's actually a replicator where we can decide, do we want to send that data to the embedded trace router and route it back on the chip and ultimately to a JTAG port, which is, it's kind of convenient to use, but that's going to be slower, lower bandwidth, higher latency.
Right.
Or most likely, we're going to want to send that stream of data out to the trace port interface unit, where we can connect an ARM D stream or a Lauterbach probe to read that trace data externally. And then all of these blocks are configured using the debug access port along the bottom. All of these blocks have different configuration settings, so you can decide exactly how you want to use that. So there's 3 things to highlight in this diagram.
Okay.
The first is shown in blue, and this is just the performance capabilities. We've got the high-speed 32-bit dedicated AXI interconnect for the FPGA data.
Okay.
You've also got 32 kilobytes in the FIFO, so that's not going to slow down or block your data.
Right.
Secondly is very precise cross-correlation. For the global time stamping, we have 48-bit precision, so you can very precisely record both the FPGA status at various clocks as well as the clocks on the processor.
Nice.
And then lastly, there's system level state awareness that feeds into the STM. And again, this is another advanced feature where you can actually record different states of the FPGA logic at certain times, or the processor at certain times. So maybe your processor is in a power down mode when an error occurs, or maybe you've just experienced an ECC error flag. All that data can be captured, that system state can be captured up to 32 states, user definable states, and that's fed into your stream as well.
Okay, cool. So, Todd, is the STMs the only way to do this?
So the STM is really the ideal way to do this,
Okay.
as it offers a high-performance, multi-core based approach for ARM A9 systems. But ARM does have other trace macrocell blocks out there, and one is an older one called the instrumentation trace macrocell, or ITM, that is in fact used in some other SoC FPGAs. Now, we won't go through all the details here on this chart, but to summarize at a high level, the STM was really designed for the multi-core, high-performance A9 systems, and so it's really just a natural fit for this type of device. The ITM was actually designed for microcontroller-based systems, which obviously are slower and less complex. And so there are ways that you can add things on top of that, maybe to get some more data out of it, but the fundamental infrastructure just isn't there. And one other example I'd like to just point out is this timestamp precision. As I mentioned, we have 48 bits in the Altera SoC FPGAs, whereas our nearest competitor has 21 bits and gives you more of a coarse grain effect. So the way to look at this is you could map those 21 bits of the clock onto the upper 48 bits, and then you'd have very large time chunks or coarse grained. The other way you could do it would be to map those 21 bits to the lower end of the 48 bits, but in that case, you're going to have very limited amount of trace data.
Right.
So having those 48 bits give you a very precise global timestamp, which greatly helps you debug your system.
Okay, cool. That makes sense. So if I want to investigate this architecture stuff in more detail, where do I go for more information?
So right, we've actually only gone through 3 major ones that I wanted to highlight today, but there's many other occurrences like this where Altera has thought through the architecture and the data flow and put these right widgets in place to make your design as best possible. And so we've got a full 39-page white paper in case you're looking for some more reading,
Excellent.
Amelia. Or we've got a design checklist that's just a one-pager that kind of summarizes these key bullet points, and then you can go investigate them one by one on your own.
Excellent. Now, this was a bit to take in all at once, so can you recap just a bit for me, Todd?
Sure. To summarize, we've seen the SoC FPGAs are indeed taking off across multiple market segments and applications. They're not just the solution of the future, they're really the solution of today as they get designed in many places by many, many customers. So the question then becomes, with this new architecture, which one should you choose? And though on the surface these may look the same in terms of the dual-core processor and an FPGA, you've really got to look under the hood and see some of these key architectural differences that can make or break your design. So today we walked through 3 of them in terms of the memory performance and the intelligent memory controller, the Snoop control unit ports on the L2 cache. We talked about memory protection in ECC, how critical those are, and then the system trace macrocell and the other features and tools that Altera has brought forth to help you get your design to the market quickly. And we put more resources that you can research, additional examples on the website here. So the bottom line is that architecture matters. You've really got to look at these details and look at these features and choose the best SoC FPGA for your design.
Well, I think that's all I have time for today. Thank you so much for joining me, Todd. It was a pleasure speaking with you.
Thank you, Amelia. It's been great.
Before we go, don't forget to click that link. There you can download a free white paper that further expands on this topic. For Chalk Talks, I'm Amelia Dalton. For more Chalk Talks, check out the EE Journal YouTube channel or the on-demand section of eejournal.com.